Our second conservation of energy problem states that the figure to the right shows a water slide ride in which a glider is shot by a spring along a water-drenched, frictionless track that takes the glider from a horizontal section down to ground level. As the glider then moves along ground level track, it is gradually brought to rest by friction. The total mass of the glider and the rider is 200 kilograms, and the initial compression of the spring is 5 meters. The spring constant K is 3.2 times 10 to the third newtons per meter, and the initial height H is 35 meters. The coefficient of kinetic friction along the ground level track is mu K equals 0.8. Through what distance L does the glider slide along the ground level track until it stops? Now, there's several ways to do this problem, and we will revisit it after we talk about, when we lose energy due to friction and what happens to that energy and things like work and stuff like that. But right now, all we're going to do to solve this problem is use conservation of energy and then Newton's laws and a little bit of kinematics also. So it's kind of bringing everything together that we've already talked about, which is exciting. It's very exciting. So, first and foremost, we have to split this up into two different motions because first motion, we're going to use conservation of energy here because we know that we have some type of energy initial at the top of the track, and then we will have some type of energy final at the bottom of the track, and we'll talk about what those two things are. Then we're going to use the force of friction that's bringing that glider plus rider to a stop in this L distance right here. So here we're using Newton's laws, so Newton's second law with friction, and then kinematics in order to find through what distance L does the glider slide along the ground level track until it stops. Okay, so two different steps here. So let's concentrate on that energy portion first. So we know that, number one, let's write down all our givens. We know that the mass of the glider is 200 kilograms. We also know that the initial compression of the spring is D equals 5 meters. I'm going to put X for this. Our delta X for the spring is 5 meters. And then it says the spring constant K is equal to 3.2 times 10 to the third newtons per meter. The initial height, H initial, is equal to 35 meters, and the coefficient of kinetic friction along the ground level track is 0.8. So I'm going to put mu K, I'm going to put that over here, 0.8, because we'll use that later, okay? Now, at the very top of this track right here, we can see that we have a certain height off the ground, so we know that we have gravitational potential energy, and then we also know that we're compressing a spring, so it's like a spring-loaded car and it's going to be shot out. So we also have some potential energy in that spring that's going to cause that car to shoot out at a higher velocity than it would have if the spring wasn't there. So because of that, we know that we have both gravitational potential energy and elastic potential energy. So two different types of potential energy. Now it also says blah, 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 blah. It doesn't specifically say this. It says it shows a water slide in which a glider is shot by a spring-drenched frictionless track. It doesn't specifically say that the glider starts from rest, but we can assume that the initial velocity is 0 because, we're loaded onto that spring and then the spring is let go and then it goes. So our initial velocity equals 0. So looking at our conservation of energy equation, we know that the initial energy equals final energy. And then if we plug in our different types of energy, we have kinetic energy initial plus potential energy initial. And I know I have both gravitational plus elastic. I'll put S for spring because that's what I had in the lecture. And then I'm just going to put all those variables too, because we haven't really talked about the final case. We don't really know what we have in that final case yet, what kind of energy I mean. So kinetic energy final plus potential energy final. And I'm just going to write potential energy final. Now, like I said, we start from rest. Now I know that the kinetic energy initial kinetic energy in general is 1/2 times the mass times velocity squared. So if we start from rest, that means we have no initial kinetic energy. So that means this is 0. Now, like I said, we know that we have both initial gravitational potential energy, which is mgh initial, because we are up at a height of 35 meters, plus we have an initial elastic potential energy as well, 1/2 kx initial squared, because that spring is compressed a certain distance x. Now, our final kinetic energy, we know at the very bottom, right here, after that glider slides down the slide like that, we are moving at a certain velocity. So we do have kinetic energy. So I have 1/2 mv final squared. Now, what about potential energy? Do we have any potential energy in this final case? Well, we're not up at a certain height h because we are on the ground now, so we have no gravitational potential energy. And also, look, there's no springs involved here. So because there's no springs that are stretched or compressed, that means we don't have elastic potential energy either. So that means that our potential energy in this case is equal to 0 in the final case. So all of that potential energy, both gravitational and elastic potential at the very top, is converted into kinetic energy at the very bottom. So this is our equation now. So we can plug in our numbers and we can see what we're trying to find. So what we're trying to find here is, first and foremost, we need to find the final velocity at the bottom, because we know that we're going to slide to a stop during that L portion, and we want to know what L is. So in order to find what L is, we first have to see how fast we're going at the very bottom. Okay, so that's why we need to find the final velocity. And I know the mass, I know the initial height, I know K, our spring constant, I know X initial, our initial compression of the spring. And so we know everything in order to find that final velocity. So here, I'm just gonna plug in our numbers. We have the mass, which is 200 kilograms, times acceleration of gravity, 9.8 meters per second squared, times the initial height, which is 35 meters, plus 1/2 times K, which was 3.2 times 10 to the third newtons per meter, times the initial compression of the spring, which was 5 meters squared, equals 1/2 times the mass, 200 kilograms, times V final squared. So we get quantity 200 times 9.8 times 35, close parentheses, plus, open parentheses, 0.5 times 3.2 times 10 to the third times 25, because 5 times 5. And then I'm going to multiply that by 2 to get rid of that 1/2 on the right-hand side, divide by 200, and then take the square root in order to find a final velocity of 32.95 meters per second. So we're not done yet. We just found the final velocity at the bottom. So we know that in this new distance L here, we have now a final velocity coming down that slide will become our initial velocity for this slowdown of the distance L. We have 32.95 meters per second for our initial velocity. Final velocity, we know that we slowed to a stop, so that's going to be 0. Our distance is L, so what we need to find here now is the acceleration. So how fast is that thing slowing down? How fast is that thing slowing down? Does that even make sense? Now, if we draw a free body diagram of this glider, we know that we have the force of gravity, normal force up, and then as it moves to the right, we have the force of friction slowing this thing down. So the force of friction is the thing that is causing that acceleration, that negative acceleration in this case. So we know force of friction is equal to mu times the normal force. And we know that this is what is causing that acceleration. So this is the only force that's causing that acceleration. So this is what we're going to plug into our net force equation. So we get force of friction, which is mu times normal force, is equal to mass times acceleration. We know normal force in this case because we're not accelerating up or down. Normal force is equal to the force of gravity, which we know is mass times acceleration of gravity. So we can plug that in for normal force right here. So we get mu times mg equals mass times acceleration. Look, the mass cancels out of that glider. And now we get that the acceleration of the glider is equal to mu times acceleration of gravity, which is 0.8 times 9.8 meters per second squared. And 0.8 was given in the problem. So we get 0.8 times 9.8, which ends up being 7.84. And so this is our acceleration. And remember, in this drawing that I drew right here, the acceleration is going to be negative because we're slowing down. So now we can use kinematics in order to find our distance L. So we know that the, again, initial velocity is 32.95, which we found from conservation of energy, meters per second. Our final velocity is 0. Acceleration is a negative 7.84 meters per second squared. And again, I know that's negative because I know that I'm slowing down, and I called initial velocity positive. So remember, when velocity is positive but acceleration is negative, then we slow down. And then we want to find our distance, so our delta x, or in this case, we are calling that L. So the equation that we need to use is final velocity squared equals initial velocity squared plus 2 times a times delta x. Plugging in our numbers here, we get final velocity squared, that was 0, is equal to initial velocity squared, 32.95 meters per second, square that, plus 2 times a negative 7.84 times L. I'm going to subtract that 32.95 squared from both sides, and we get a negative 1085.7 for that. And then we divide by a negative 2 times 7.84, and we end up getting that our L distance is 69.24 meters. And that's going to be the distance that it takes that glider to slide to a stop in that frictional area.